Okay, let's get started, please. So, can anybody remember what we are doing? Eigenvectors? Eigenvectors, eigenvalues. How do we get them? How do you get your eigenvectors and eigenvalues? Characteristic polynomial, right? So you've got this, you start out with your matrix, you look at the determinant of the matrix minus lambda I, right? That gives you this polynomial, and then you factor the polynomial somehow and get its roots, and then those guys are your eigenvalues, right? Right. Once you have the eigenvalues, how do you get the eigenvectors?
Find a null space.
Find a null space of, A minus your eigenvalue times I, right? And that will give you the null space. That will give you the eigenvalues, eigenvectors. Excuse me.
So it has to be a square matrix.
Has to be a square matrix because you're talking about the determinant.
Yeah.
Right.
Is there like anything analogous with like non-square matrices?
Yeah, you can look at the yeah, and in fact, that's sort of what we'll get to with the singular value decomposition in some sense. But yeah, you have to look at like A transpose A or A transpose, say, and that will give you a square matrix. Okay, yeah. Okay. Yeah, so you should also notice that when you have the characteristic polynomial, then you have to find the roots of the characteristic polynomial. And in general, this is impossible, right? Because unless you have something degree 5 and under, then you have no hope. Okay. That is, finding the roots of a polynomial is not easy. There's no quadratic formula for things of degree over 5. Okay. Okay. So should we start with? I made the other class start with an exercise, but I think just the talking at the beginning probably is enough to get you where I want you to be. Okay, so let's start off with, so remember, I'm just going to write a little bit of what we just said, that the eigenvalues of a square matrix are the roots of the characteristic polynomial, which is the determinant of A minus lambda I, right? Are the roots of the determinant of A minus lambda I. Notice that this thing is a polynomial, right? This thing, characteristic polynomial, has degree n, right? It's an nth. The degree is n, right? You're going to have lambda to the n. Lambda to the n is your highest degree. Okay. That's just a side remark.
So how there's degree of?
The degree of the characteristic polynomial is n. The degree of the characteristic polynomial is n. Okay. So I'm going to make some observations, some simple observations. Okay, and the first one is like this. If lambda is a complex number, is an eigenvalue of A, then lambda bar is also. Okay. Now, I don't think we defined what lambda bar is. Did we mention it? No, okay. Okay, sorry, we did in the other class. It's something called the complex conjugate. Okay, so you have complex numbers, right? So complex numbers look like this, right? A plus bi. A plus bi. I is, a square root of -1. Right? And so you can represent them on a graph, on a plane, by thinking of one axis as the real axis and the other axis as the imaginary axis, right? So, right, this guy would be A plus bi. Here's A, and here's bi, right? Okay, so you use the y-axis to represent the imaginary part. Okay, so this, if you want to draw your complex numbers, you can draw them on the complex plane. Okay. A minus bi is called the complex conjugate of A plus bi. Okay. So C bar is called, so if Z is A plus bi, then A minus bi is called the complex conjugate of Z. Excuse me. Complex conjugate of Z. Okay. And you notice what it is. It's the reflection of your point across the real axis. Okay. The reflection of your point across the real axis. Okay. Okay. Are there any numbers that when you take the complex conjugate, they don't change? Real numbers, right? If you look on this graph here, you look at this picture here, right? The only things that when you reflect them don't change at all are the guys that lie on the real axis to begin with, right? Right? If Z is just A, right? If Z is just A, well then you got A plus 0 bi. That 0 bi becomes negative 0 bi. And 0 and negative 0 is 0. Right? Okay. So notice that you're equal to your complex conjugate if and only if Z is a real number. Right?
Is an asterisk used sometimes? That's really used in quantum mechanics.
Physicists.
No.
Yeah. I've never seen it that way. Yeah, I've never seen it. Yeah, it must be some physicist thing. Yeah. Okay. So I guess we don't have a space here. Okay. So let's see. So let's make an observation. So observation. If P is a polynomial with real coefficients, then if lambda is a root of P, then lambda bar is also. Okay. In other words, complex roots occur in conjugate pairs. Complex roots occur in conjugate pairs. Whenever you have one complex root, its complex conjugate will also be a root. Okay. Let me explain this observation by giving you an example. Okay, so I think it'll be clear if you think about this example. Okay. So look, consider the polynomial x squared plus x plus 1, right? It has real coefficients. Okay. So you've got this polynomial, it's got real coefficients, and let's say that lambda naught is a root. Right? Suppose you have one root of this guy, well that would mean that lambda naught squared plus lambda naught plus 1 equals 0. Okay, everybody all right? Okay. Okay, then let's take the complex conjugate of both sides. Okay, this thing on the left is 0, the thing on the right is 0. We take the complex conjugate of both sides. Okay. Well, what's the complex conjugate of 0? 0, right? What's the complex conjugate of a sum? Well, it actually turns out to be the sum of the complex conjugates. Okay, right? That sort of makes sense, right? If you add things together and then flip them over, it's the same as if you flip them over first and then add them, right? Similarly, if you multiply things and then flip them over, it's the same thing as if you flip them over and then multiply them. Okay, so what this boils down to is that this is going to be the complex conjugate squared plus the complex conjugate plus complex conjugate of 1, which is just 1. So we're sort of cheating you because we're using the fact that the complex conjugate of the sum is the sum of the complex conjugates, but that's sort of intuitively obvious. And then the complex conjugate of a product is the product of the complex conjugates, which is not so intuitively obvious unless you know what complex multiplication is geometrically, in which case it is obvious. But for that, you have to wait for some other course. Or if we have time at the end of the term, I'll show you. Yes. Okay, so what do you see? Look, if this guy is a root, then this equals 0, but then this equals 0, right? But that means that this guy is a root. Right? So if somebody is if you have a complex number that's a root and your coefficients are all real, then its complex conjugate is going to be a root also, and vice versa, right? If this guy is a root, takes a complex conjugate, come back to here, this guy's going to be a root. Okay. So complex roots occur in conjugate pairs as long as you have a polynomial with real coefficients. That's key. Okay, so now let's get back to simple observation number 1, which was that if A is a real matrix and lambda is an eigenvalue, then lambda bar is an eigenvalue. But now that's just a consequence of what we just said, right? Because to be an eigenvalue means that it is a root of the characteristic polynomial, right? Which is a polynomial with real coefficients, right? And so we see that that happens if and only if this is a root of the same polynomial. Okay. Which is to say that lambda bar is an eigenvalue.
I assume eval is eigenvalue.
Yeah. So if I write eval or e vector, it means eigen. How about you looking skeptical?
There it says that the determinant of a minus lambda I is always a polynomial with equal.
Sorry. It's bad. It's very bad notation.
So, is it always the case that the determinant of a minus lambda I will always be a polynomial with real coefficients?
Yeah.
What if a had like a complex number? Does that never happen?
A is a real matrix. A is a real matrix. Okay. I see. You weren't scowling about the bad notation. You were scowling about this fact.
I was looking at that.
Yeah, because you've got it. Yeah, and it's false otherwise.
Oh, so if we had a matrix made of complex numbers, then that wouldn't hold.
Not going to hold. Yeah. Right, because we needed a real we needed a polynomial with real coefficients. That doesn't happen. Okay. Okay, I seem to have run out of space. Okay. Simple observation number 2. Now let's say that you have a pair of complex conjugate eigenvalues. Then you are an eigenvector of one eigenvalue if and only if your complex conjugate is an eigenvector with respect to the conjugate eigenvalue. Okay. So when I say the conjugate of a vector, I mean that you take the complex conjugate of each of the entries. Okay, so this vector is now a complex vector, right? It has n components, each of which is a complex number. Yeah, Mariah? No?
No, sorry, continue.
Okay, right, and then this thing over here would be the complex conjugate. You just take the complex conjugate of each entry, right? So like if this vector is, right, suppose this vector looks like, like 1 plus I. V bar would be 1 minus I, negative I, right? The complex conjugate vector. You just take the complex conjugate of each entry. Okay. And so what we're saying is that the eigenspace corresponding to this eigenvalue and the eigenspace corresponding to the conjugate eigenvalue can be obtained from each other by taking complex conjugates, right? Anybody in here is the complex conjugate of somebody in here. Okay, that's sort of what you would expect. Why? Why? Well, think. If V is an eigenvector with eigenvalue lambda, that's equivalent to saying that AV equals lambda V. AV equals lambda V. But then you take complex conjugates of both sides. You take complex conjugates of both sides, and you get, using the rules of complex conjugation, that you can break it down like this. Okay. So it's a little bit cheap because I'm expecting you to like say, oh yeah, okay, that's, that makes sense, right? I'm afraid, just trust me, it actually is true. Okay, it is true. That, when you take the conjugate of a product, it's the product of the conjugates and the sums. Okay, but then here you're taking the conjugate of a real matrix, right? So this is just A itself, right? The conjugate, if you're conjugating everything in the matrix, and the matrix is real, sorry, I didn't say it again. So you got this real matrix, you conjugate everything, well, nothing changes. Okay, but you see what happens, right? So what you see is that V bar is a eigenvector of A with eigenvalue lambda bar. Right? That's what this says here. Right? V bar is an eigenvector with eigenvalue lambda bar. Okay, everybody all right? Okay, so this is we're just making some observations about eigenvalues and about complex eigenvalues and their related eigenspaces. We'll need these facts later on. Okay. The last thing in this chapter is what I would call a not so simple observation. So in fact, if we want to prove this not so simple observation, it will probably take the rest of class to prove. So I think I'm going to skip it actually, because I've proven it in previous years, and we spent like the whole class on this one proof. But I don't think that it really improves your. It doesn't really help people that much. So I'm going to skip it this year. I'm going to tell you what it is, but I'm not going to prove it. Okay. If you're interested, I can show you a link to what I did to previous years. Okay. But I don't think it's worth the time. We can use our time better in getting on to the next section. Okay. So but the observation itself is cool, even though the proof is maybe not that illuminating. Okay, and here it is. So if you have a n by n matrix, and you have lambda 1 through lambda n, the roots of the characteristic polynomial. In other words, the eigenvalues of A. The eigenvalues of A. Maybe with so some may repeat. Right. If you have a double root, we're gonna write it twice. Right. Maybe your characteristic polynomial looks like this. Right. Then in that case we would have 2, 2, and 3 in our list here. Okay. Okay. So you have all the roots. Some of them may be repeating. Then something cool happens. The determinant of A turns out to be equal to the product of the eigenvalues. Okay. The determinant of A turns out to be the product of the eigenvalues. And 2, the trace of A turns out to be the sum of the eigenvalues. Now, I think we haven't introduced what the trace is, so maybe the second fact is not that interesting. But the trace is defined as the sum of the diagonal elements of trace of A. the sum of the diagonal elements of your matrix. Okay, so this is pretty cool. So, for example, if you have a matrix 6, -4, 3, -1, well, you can calculate that the determinant of A is 6 and the trace of A is 5. The determinant of A, you work it out, turns out to be 6. The trace of A, 6 minus 1 is 5. Okay. But we did the eigenvalues of this the other day, right? Recall, the eigenvalues of A were 2 and 3. Right? And you see that 2 times 3 is 6, the determinant, 2 plus 3 is 5, the trace. Okay. And that's not a coincidence. That's always going to happen. Right? If you get the list of eigenvalues, then that gives you both the determinant and the trace of your matrix. Okay. But the proof of this, again, I don't think is particularly illuminating. So we're not gonna do it.
Is it like how, because like when you multiply by lambda I, it only affects like the diagonal elements?
What do you mean when you
Like,
multiply?
sorry, like A minus lambda I, you only subtract from the diagonal elements.
And so,
Well, yeah, I guess. Could you do the determinant?
yeah, it's not so straightforward to understand, actually. Yeah. Yeah. Okay. 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 Okay, so let's go on to the next section. Actually, not the next section, but the section after it. So 6.3, diagonalization. Diagonalization. So we're going to skip 6.2. 6.2 is basically about a trick for solving differential equations. I know some of you look like you want to see it. Maybe we'll come back to it. Okay, so if there's time at the end, if we manage to get through singular value decomposition, I promise we come back to 6.2. But singular value decomposition is far more valuable than the trick for differential equations. So let's try and get there. Okay, so diagonalization. Basically, we're going to try and find a way to make our matrices diagonal. So let's start off with the following observation. Suppose you have an n by n matrix, and lambda 1 through lambda k are distinct eigenvalues. Eigenvalues of A. Let's say that lambda 1 through lambda k are distinct eigenvalues of A with eigenvectors v1, do the VK. Okay, so none of these guys are the same. None of these guys are the same. We've thrown out any duplicate, any repeated roots. Okay. Then the VI are linearly independent. Then the VI are linearly independent. Okay. Okay, so this is saying that if you have eigenvectors, you've got eigenvectors corresponding to distinct eigenvalues, then that set of vectors is linearly independent. Okay, you're guaranteed that these eigenvectors are linearly independent. Okay, let's give a corollary of that first. So there's a useful corollary which says that, well, look, if A has n distinct roots, right? I'm sorry, the characteristic polynomial right? If the characteristic polynomial has n distinct roots, well, then what's going to happen? You're going to have n eigenvectors that are linearly independent, and so you're going to have an eigenvector basis, right? Right? Then you're guaranteed an eigenvector basis. Right? You can find a basis of eigenvectors. Okay. Right? There would be some basis, right? So you'd have right? You'd have you've got your distinct roots, and then you would have n vectors where they're all eigenvectors, a, b, I equals lambda I b I. A b I equals lambda I b I, right? So all eigenvectors, and you'd have an eigenvector basis, right? That's great. Yeah, Mariah.
Is it a basis of R?
Yeah,
Okay.
right, because you'd have n vectors, right? You would have n vectors in Rn that are linearly independent, right? And because you have n linearly independent eigenvectors. Okay. What's good about having an eigenvector basis? What's good about having an eigenvector basis?
You get a diagonal.
You get a diagonal matrix. How do you get the diagonal matrix?
Make that your matrix representation.
Exactly. I'll give you 2 points on the fun for just saying that. Okay. As long as I remember to. Sometimes I forget, I have to admit. So yeah, maybe send me a note. Send me a note saying, Professor, oh, don't forget. You said this. Sometimes I forget. Okay, so yeah, right? Because you know what's going to happen, right? You've got Rn, right? You got your matrix A, right? You got your matrix A. Oops. You got your matrix A, and then you get your matrix representation A prime, say. Okay. Does anybody remember how to get A prime? You start off with your basis. Remember what you do? You start off with your basis. You
Get the coordinate.
get the coordinate vector of So you take A, B, I, and take the coordinate vector with respect to B, with respect to the B basis, right? Right. So, right. Right. So this thing has columns A, B, I with respect to the B basis, right? But what's ABI? ABI, these guys are eigenvectors. So ABI is just going to be lambda IBI, right? Lambda IBI. What's lambda IBI with respect to the B basis? How do you represent this function as a linear combination of the BJs? It's going to be just 0, 0, 0, 0, 0, lambda I, 0, 0, 0, 0, 0, right? So this thing is going to be lambda I, right? It's going to be 0, 0, 0, 0, 0, lambda I, 0, 0, 0, 0, 0, right? And so you see what the matrix is going to look like. These are the columns. It's going to be the matrix where the diagonals, it's a diagonal matrix with the diagonals being the eigenvalues, right? Right. So knowing, using your previous knowledge, right? Having an eigenvector basis gives you a matrix representation that's diagonal, right? Gives you a matrix representation that's diagonal. It's going to look like lambda 1 through lambda n. Let's come backwards to this fact that that sort of opens the door to us possibly having an eigenvector basis. So let's go back to this theorem, and it says that that if you have eigenvectors corresponding to distinct eigenvalues, then they form a linearly independent set. So here's how we're going to do it. We'll say, well, suppose they are dependent. Suppose that V1 through Vk are linearly dependent. In other words, that the span has dimension that's smaller than k. Okay. Suppose the dimension of the span isn't k, right? That there's some dependence between the VI's. Okay. Okay. Well, rearrange them. Rearrange the order so that V1 through VR are independent. Okay. But you know that there's going to be R guys who are independent there. Make those guys the first R guys. Okay. So just rearrange the order. Okay. And so that V1 through VR plus 1 are linearly dependent. Okay. And we'll see that we can get a contradiction. So proof by contradiction. Suppose that they're dependent. Okay. So say, okay, Everybody all right? Okay. So you say, okay, well, these guys are linearly dependent. So since they're dependent, since these guys are dependent, we know that there exists coefficients C1 through CR plus 1, not all 0, such that C1 V1 plus C2 V2 plus CR plus 1 VR plus 1 is the 0 vector. Yeah, Eric.
Could you explain why V1 to VR plus 1 are linearly dependent? Shouldn't be VR to VR?
Speaking of upward starting one.
So we suppose that the span is R. Suppose that span is R dimensional. Okay. That means that we can find these R guys who are independent, and then if we throw one more in, it becomes dependent.
Oh, okay.
Okay. Yeah. So we throw in one more, it becomes dependent now. Okay. Well, the R plus 1 guys are dependent, so we can make a linear combination that gives you the 0 vector, right? And now we're going to mess around with it a little bit. We say, okay, well then, if I multiply the whole thing by A, right, I get the 0 vector. I multiply both sides by the A matrix. But that gives me, using linearity, C1 A V1 plus C2 A V2 plus CR plus 1 A VR plus 1 equals 0, right, by linearity. Right? But remember, each of these guys was an eigenvector. Right? The VI are all eigenvectors. So this says that C1 lambda 1 V1 plus C2 lambda 2 V2 plus CR plus 1 lambda R plus 1 VR plus 1 is the 0 vector. Okay. Now, let's take this equation here. Okay, let's take this equation here and multiply it by lambda r plus 1. Okay, multiply the whole thing on both sides by lambda r plus 1. We also, from star, we get that C1 lambda r plus 1 V1 plus C2 lambda r plus 1 V2 plus CR plus 1 lambda r plus 1 VR plus 1 equals 0. Right? What am I going to do next? Subtract. Right? So subtract the lower from the upper. Right? We get right? These last guys will cancel off, right? And we get C1 lambda 1 minus lambda r plus 1 V1 plus CR lambda 1 minus, lambda r minus lambda r plus 1 VR equals 0. Right? Why does that give us a contradiction?
V1 to VR.
V1 to VR are linearly independent, right? So that would mean that
Not 0 vector.
that the only way to get 0 is if all these guys are all 0, right? But what do we have here? Notice that, call that not all CI are 0. Right? Not all the CIs are 0. And further, we also have that also all eigenvalues are distinct. Right? All the eigenvalues are distinct. So we know that these terms are all non-zero. Right? These guys are all non-zero. Right? But that means we have, right, since these terms in the parentheses are all non-zero, and the CIs, some of the CIs are non-zero, at least one of the CIs is non-zero, then we have a combination yielding the 0, we have a non-trivial combination yielding the 0 vector. Right? So, so we see that V1 through VR are linearly dependent. Okay, and that gives us contradiction, right? Because they were supposed to be linearly independent, right? The guys through V1 through VR were supposed to be linearly independent, but we were able to make a non-trivial linear combination of them yielding the 0 vector, which means that they're dependent. So contradiction.
So what's that? The symbol?
That's the contradiction symbol. So like contradiction. Some people use this symbol. I've seen both of those things, or they just write contradiction. But I like this symbol. It's kind of cool looking. Okay, so next time we'll go more into diagonalization, and so that's it for today.